Hello again, this is Rob, and I hope class is going fine. I'm just going to do a quick recap of section 5.4. Again, I know Chris McClure is doing an excellent job, so you probably don't need these videos, but just in case. Section 5.4 was all about finding the area underneath a curve using the fundamental theorem of calculus, and that sounds confusing, but really it's the exact same thing that you've been doing in section 5.3. We're just going to evaluate the integrals after you integrate. So again, we're going to be finding area underneath the curve. There's a lot of theory here. I'm going to skip past a lot of the theory, and I'm just going to get to quickly to the examples. We'll even talk about average values, even and odd functions, and some annuities that's just going to be applicable to you business majors. So first of all, to find the area underneath the curve, we're going to integrate over the area between A and B. So this is kind of a unique area because it's called the area underneath the curve. You couldn't do this before you had calculus, but the integration rules allow us to find the area underneath the curve, such as this. So A is called the lower limit. We always put the lower limit on the bottom and then the upper limit. And then to find the area, we always do the upper minus the lower, which I'll talk to you in a moment, or f of B minus f of A. So let's start out with a really simple example. This is the line y equals 2x. And to find the area underneath the curve here, I probably wouldn't spend a whole lot of time integrating because you can see it just forms a nice little triangle. I would probably cheat and use geometry. The area of a triangle is 1/2 base times height. Again, finding the fastest way to solve for this. The base looks like it's a 2. And the height looks like it's, so let's go for 4. And so it looks like the area underneath the curve, which is not even a curve, is 4 units. Yeah, the author did the same thing. It might be useful to go through the integration rules and show you how to do that problem again using calculus instead of just using some geometry techniques. So again, we're talking about the area underneath the curve. That delta x, it's pronounced delta x, is the change in x. So you can see we're going to talk to today about this x distance and x plus some change in x. And the change in x is really just the width of any rectangle. And so the goal here, again, a lot of theory that goes in here, but I could throw a bunch of little rectangles in here and try to approximate. This would be approximation underneath the curve. This would be the approximation over the curve. Can you see the rectangle goes over? And then they're saying the area is actually somewhere between underneath the estimation. This is the lowest that it could be, and this would be the highest that it could be for the estimation. So we know that the exact area lies somewhere between those rectangles under or those rectangles over. And again, but I wanted to point out to you, this is just the width of the rectangle. Again, a lot of theory, but the only thing I really want you to point out here is after you evaluate, we're going to plug in the b and then subtract off the a. So it's this rule, f of b minus f of a. I'm sure Chris went over all the theories. Oh, there it is, the fundamental theorem of calculus, f of b minus f of a. Is the rule. It's kind of nice. We don't have to worry about the constants because if you do the f of b minus f of a correctly, your c's will just cancel out. Here's the example. If you integrate x cubed, you get x to the 4th over 4. And notice that they're going to integrate that. F of 3, so this becomes 3 to the 4th divided by 4, and then minus f of b is the rule. So again, once again, let's look at, oh, this is nice too. If you have another point, point B, so maybe you don't want to go from A to B, you can find another point in between called point C that would break up the interval a little bit more. So instead of talking about A to B, finding the area underneath that curve, you could just go A to C, find that area, and then add C to B. And that's what they're doing. They're just saying, hey, you can use those integration properties and break that up. Of course, if you just go A to A, that area is going to be, there is no area. It's just a linear function, vertical function. Oh, and this is kind of nice. Sometimes we have to switch the lower numbers. I'll show you the case that you have to do that. But instead of going from A to B, if you decide that you need to go from B to A, the opposite direction, well, you just throw a negative out front, and that is the opposite. We do that in certain cases, which I'll show you in a moment. So here's that exact same problem that we had before that I cheated and used the area equals 1/2 base times height. But this time, let's try to integrate. So I've got a constant. We'll throw the constant out front. I'll say 2 times the integral from 0 to 2 of just x. Let's integrate. Integrate means increase, so this 1 goes to a 2. X squared, I'm going to divide by 2, and of course, that's how to integrate x to the first. It's all of this. But I have a 2 sitting out front still, and so when I multiply by 2, I get x squared. Of course, the dx goes away. And I'm going to evaluate that from who? Well, it said evaluate it from 0 to 2. Let's do my f of b minus f of a. If I plug in the b term first, my f of b term is x, no longer x. I know what x is. X is 2. So let's go 2 squared minus my f of a term. And in this time, the a term is 0 squared. And sure enough, I get the exact same answer 4 that we had before when we cheated and used the area formula. It's really not cheating. It's just the fastest way to do it. But the area of a triangle is 1/2 base times height. Well, this one, it's kind of close to the area of a triangle because the curve isn't really steep. It's almost linear, but it's not linear because I can see it's an x squared function. So for this one, I really do want to integrate between where? Put the lower number from A is going to be 1. The lower number always goes in the bottom. B, and I'll do x squared minus 1. The same process. So I'll just set it up like this. Let's integrate. To integrate x squared minus 1, I'm going to integrate, well, I can use my integration properties and integrate the x squared and subtract off the integral from 1 to 2 of just 1. So to integrate x squared, I increase by 1. It becomes x cubed divided by 3. And minus, this becomes what? Increase this x to the 0 by 1. Just x. Well, you can always check. The derivative of x is just 1. But I'm going to evaluate that from where? From 1 to 2. So this time it gets a little bit more complicated, but I'm going to evaluate f at b first, but I need to plug in the b term twice. Now here comes the trick. You need to do f of b minus all of f of a. Oh, they're just telling you underneath this box. This is integration to find the area underneath the curve, which I have written right up here. So here we go. Let's evaluate at the 2. So this becomes 1/3 of my b, which is 2 cubed minus 2, minus all of my f of a, and I would use these parentheses if I was you. So if I plug in the 1, I get 1/3, well, 1 cubed, I'll write it so you can see it, 1 cubed minus 1. Let's see if we can evaluate this. Let's see, 2 cubed is 8. Oh my gosh, here we go. 8/3 minus 2. Let's change 2 to, how about 6/3, just so I have a common denominator. This is just 1/3. Let's keep the parentheses for a little bit longer. 1/3 minus, so let's say 3/3. Again, changing that 1 to be a common denominator. So 8 minus 6, let's go for 2/3. Minus, in parentheses, oh, I have a negative 2/3, which is 2/3, really plus 2/3, which is a whopping 4/3. We'll see if the author worked it out. Yeah, the author got 4/3 as well. So again, there's the first example of integration. Let's try it again. Evaluate the indefinite integral. Can't break this up into the integral of 4t plus the integral of 1 because the whole thing is being squared. So perhaps the best thing to do here is a u substitution because I see an inside function and an outside function. So I wonder what would happen if I let u be 4t minus 1, or excuse me, plus 1. Then du would equal 4. Dx, and I notice that I don't, oh, actually it's not even dx, it looks like it's dt because all the variables are in terms of t instead of x. So this is 4 dt. So I'm going to replace 4. I don't have a 4. Well, let's divide by 4. So I can just replace dt with du divided by 4. All right, we'll see if this works. So I'm going to integrate. This is my u. Let's see, a u squared. And I'll replace this dt with du divided by 4. And of course, I could pull out the divided by 4. That's that 1/4. And this is my du term now. Instead of du divided by 4, I just pulled out the 1/4. So I increased the u by 1, and the 2 goes to a 3. I'll divide by that. Drag on the 1/4. I wonder if I can multiply this 1/4 times 1/3 and just get a 1/12 out front. And I'm just going to evaluate. Let's see, let's replace this u back with 4t plus 1 quantity cubed. And I'm just going to evaluate this between where? 0 and 1. So I'm going to keep that 1/12 out front, make my life just a little bit easier. So it's 1/12 times f of b. If I plug in a 1, I get 4 plus 1 is 5 cubed. 5 cubed is 125. I'll do that's my f of b. Let's do the f of a. 4 times 0 is 0 plus 1 cubed is plus, oh, well, it's f of b minus f of a. So let's change that to f of b minus 1, which is 1/12 of, let's see, 124 twelfths, which I believe reduces to if I divide by 4, 30, 31, I don't know, 31 thirds? Yeah, 31 thirds. All right, good. Oh, and the author did a little bit different again. He pulled out a 1/4. I pulled out the 1/12. But it did look like he's, yep. He kept that out front. So he just evaluated this inside function as well. I just pulled out the 3 as well. And you can do that with constants, just not variables. Okay, oh my gosh. So here we go. Example number 4, several more opportunities to integrate. This would be a u substitution. I'd let u be, well, let's do that rule that we've been practicing. Let's see. If I let u equal 2x, then du is just 2 dx. But since you don't have a 2, we'll divide by 2. So we'll get du divided by 2 equals my dx. So I'll replace this, the integral of e to the u, integral of e to the u. Well, and dx gets replaced with du. Well, I'll pull out the 1/2, and we'll just say du. And the integral of this is just itself, because the derivative of e to the u is e to the u. But I'll replace the u substitution. U is really 2x. The du goes away. Evaluated between who? 0 and 3. So just as before, I'll leave that 1/2 just kind of dragging out front. 1/2, and now I'll integrate. Throw in the 3. This becomes e to the 6th minus, throw in the 0, e to the 0. Oh, I remember e to the 0 is 1. How do I want to write this final answer? I don't know. I wonder if I don't know. Do you want to distribute? Should we leave it? Let's see what the author decides. Oh, he just punched it. Crazy. All right. Well, interesting. So they went to decimal form. You also could have left it, if they want the exact answer, 1/2 e to the 6th minus, and remember this is just a 1, so minus 1/2. So if you punch this, this has got to be a decimal approximation. They had to have rounded. Pretty good for me. All right, so that's the introduction of this. email me with questions. Thanks.